So yeah, hello. Thank you very much for having me, and I hope this is useful to you. I wasn't obviously at your previous talk, so I hope that I don't cover old ground, as it were. I've split the talk into two because I think there's some things that Passive House can tell us for existing buildings, and it's useful. But there's also other things that are really important, and it's not maybe the answer always. So I've split it. I thought I'd start with a bit of context and the sort of retrofit problems we've got, or the challenge, and then I'd talk specifically about Passive House, what it is, so you've got some background on it. I've kept it quite high level, but I'm really happy to answer technical questions or dig into more detail in the question and answer session. So that's the idea. Cool. So about me, yeah, I'm Will. I did do an IMechE course, although I'd say the construction and the part of construction I'm in is at the very sort of basic end of engineering. But it's interesting because it brings a lot of the like people challenges, which I'll get onto as well. There's like a lot of interpersonal challenges and trying to get these technical subjects understood by more people. As in the intro, Passive House is mentioned a lot, but ultimately we just use that as a way to get outcomes. We see it as a really good process for getting towards the sort of buildings we need to deal with the future, basically deal with our future climate. Because I didn't mention who I work for either. So I work for Etude Consulting. We're a really small company with 20 people, and we've been going about 12 years. And I've been there for 12 years, so sort of part of it. And we've come out of very much larger mechanical engineering practices, so from Hawley, and then grassroots sustainability, a bit more sort of hair shirt wearing. And we really identified that sustainability engineers needed to be at the table in design teams, not just a sort of building simulation house, and that also we could be more proactive and sometimes we second guess the clients. We weren't answering the questions that we were asked. We were sort of guessing what they could afford or guessing what they wanted to do. So we're really very much like, if you want to deal with climate change, this is what you need to do. That's how we operate. Okay, good. So just two sort of slides to kick us off. So this is the total energy supply and demand into the UK via the national grid as a Sankey diagram. So you've got everything in on the left and everything out on the right. And electricity is the red bit. And this is from the national grid, so they sort of manage our electrical network. This is 2023, so last year. And then this is 2050, so this is where we're heading. And you can see the sort of huge electrification of pretty much everything that's going on. And the National Grid have been planning for this for, 20, 30 years. They're probably one of the better national bodies who are really, they've seen everything coming. They've got some good planning on the way, and they're very much sort of in control of what's going on. So that's great. We're on this last one. So we deal residential, includes some offices, and then into industrial and commercial. So these sort of top two bars. And you'll see that the sort of total there goes down quite a lot. So that's the energy efficiency. That's the bit I'm interested in. Also linked to heat pumps. So electrification of heat gets us some efficiencies there. But yeah, there's also energy efficiency. And then also the proportion that we're getting from electric rather than gas is huge. And that's, there will be some hydrogen, there will be other fuel technologies, but ultimately buildings are very low grade heat, simple stuff. We need to be doing that with what we've got loads of and is really cheap. And then the high grade expensive stuff, we might still want to fly, we might still want shipping, we might still want to make steel. So all those things are going to involve much higher grade heat, which will come from the sort of more specialist fuels. So good. Putting that into the sort of UK context, we've got net zero, whatever this means, by 2050. Actually, it's not really about achieving net zero by 2050. It's about not emitting too much carbon into the atmosphere. And a much clearer way of visualizing that is through carbon budgets. So saying by this amount of time, we cannot have emitted this, this amount of carbon. If we leave it late, if we sort of just business as usual and then drop off a quick cliff at 2050, we've emitted a lot more carbon overall than we would off if we had this steady decline. So the Committee on Climate Change set these climate budgets for shorter time periods. And at the moment, we're not completely on track, but we're not off track. And that's been almost entirely led by the decarbonisation of the electricity grid. So removing coal, removing oil, moving to natural gas, and now increasingly offshore wind, which we're really blessed with in the UK. We've got area to amount of sea we can put offshore wind on. We're very, very, very lucky if you look around the world. So we've got some shallow seas. That's good. The trouble is the sort of amount that decarbonisation of electricity can add in is running out. They're sort of doing all their job, and we need other industries to catch up, notably transport and buildings, construction industry, and not only new buildings, but existing buildings, which you might have heard before. So here's an existing building, and these are the sorts of things we're talking about. So this is just a house, a terrace house in this case, but it's very similar for wherever you'd go, and I'm sure you're familiar with many of these things. Ultimately, the only thing we really need to do is electrify heat. So really the red bit, the air source heat pump, that's the sort of key technology. Practically, that becomes difficult because we've got an existing electrical supply to every single house. It's about 100 amps, sometimes 60 amps, sometimes even 30 amps, which is quite small. So even with 100 amps, your maximum heat pump size is about 14, 15 kilowatts. So there's a sort of limit to how much heat we can get from the air source heat pump. Interestingly, that does most homes, and I'll come on to that. But to make sure that we can do all homes, and to make sure that we don't increase the cost of heating for people, and to make sure that we at the same time take some advantages and maybe improve comfort, improve internal environments, there's more things we can do. So I'll just quickly whiz through these on the slide, sort of in order of importance. So the simple wins, which we've been talking about, probably since the 90s at least, loft insulation and double glazing, those old favourites, doing it well. They're a simple change, and increasingly you can do them in a very sensitive way. People don't really notice. And then sort of ramping up a bit, maybe there's some additional wall insulation, so either external wall insulation on the outside of the fabric or internal wall insulation lining the inside of the walls. And then lastly, maybe we try and improve the floor insulation. So that's that sort of insulation part wrapping the box. Once we've got the sort of warm coat on, the important thing is we need to do it up. If we don't do up the coat, then we're still going to get cold, and that's because of air movement. So bringing cold air into the home for ventilation or unwanted air. So further things are to try and control air movement through looking at reducing drafts, infiltration, and then necessarily, because we've done that, introducing some active ventilation. So all those parts fit together to essentially reduce our heating energy and provide it through electricity, sorry. So that's the sort of aim and the outcome. The last piece on the puzzle there is some solar panels. That's a nice to have in a way on buildings. We need them at a UK scale, but really that's the sort of energy generators problem. And for homes, it can really reduce your running costs, and that's why they're sort of quite popular and becoming more popular. They are still relatively cheap. They've got good payback, maybe 8 years or so. And if you're a high electricity user, or you're a daytime user, or you can flex when you're using electricity, which again we'll come back to, then they can really drop your running costs. So for new buildings, we're sort of proponents of that. So that sort of shows you what it is. I'm sure you're really familiar with a lot of that already. You're probably looking for more detail. So this is my house, and this is putting a heat pump on an existing house, and I've made some changes, replaced the windows at the back and did the floor insulation, some upgrades elsewhere, and I have a 5 kilowatt heat pump running in there. Busy trying to persuade my neighbours to do the same, because the interesting point is going to be when the district network operator UK Power Networks, or I don't actually know who it is in Essex, get worried about it, because I said the National Grid were doing a great job of decarbonising, making a plan. The networks, they've got a difficult job, but they're not doing a great job. They're very much reactive. At the moment, the upgrades are happening either because something's broken or because there's a new building and they can leverage some cost. So yeah, there's going to be a moment where, 6 of my neighbours choose a heat pump. Suddenly, does the gas supplier maintain the gas grid? Don't know. It could cost them more than it's worth. Does the electricity supplier need to update the cable? Well, yeah, they possibly will. Probably not our cable on the road, but maybe upstream they will need to somewhere. So there's some like threshold moments coming which need some planning. Interestingly, National Grid aren't really too worried about building heating. They're worried about electric car charging, because they don't know where you're going to do it, and anyone can put a charger in, and it's much higher peaky, and it's very hard to predict when people charge. So that's quite interesting actually. The building heating isn't so much of a problem. Good. So again, I think your previous talk you said was on heat pumps, but there's 3 more slides on heat pumps. So this was a little study on housing in Cornwall, and to sort of show the council that a lot of the buildings were already heat pump ready, we call it. So you could install one tomorrow and you'd be fine. So the way we looked at this is in a number of ways. The primary things you need for a heat pump are this electrical supply, a heat load that isn't too high because of the electrical supply, and to get sort of cost neutrality, you want the heat pump with some efficiency, which means a lower flow temperature is really useful. So the things you've got to play with on a building are the efficiency, which I've sort of described, which is related to the size and the fabric of it, and then also the radiator sizes. So if you have a very leaky old building, you can put massive radiators in, loads of heat emitter surface area, and still run a low flow temperature and still heat the building. So you've got those 2 parameters, and people quite often forget the radiator sizing one. So you've got energy efficiency and radiator size. And then for the fabric efficiency, because we don't know an awful lot about buildings, which is a travesty, by the way, EPCs are rubbish. The only real data we've got on mass, it's getting better, but the only real data we've got on mass reliably are EPCs, and a lot of it is out of date. So we've taken, and through a lot of modelling, we know that fabric performance is roughly correlates to square meterage floor area and the age of the property. So that's a very broad brush assumption. And what this graph does is it plots those 2 things, floor area up the side, age of the property down the side, and it says everything below that black line is heat pump ready. The ones which are more in the yellow, there's a risk that they'll cost more to run. And the ones that are in green, they should be the same or less actually. So that's sort of showing that sort of proportion of homes. Yeah, and it's a likelihood thing, but it's traffic light scale to make it simpler. That just sort of visualizes the properties. You can put a bit more detail to it and sort of do some statistical analysis. And this looks at just, okay, how many of those different types of home are there? So smaller homes got a sort of normal distribution curve. Most homes are in the 70 to 100 meters squared size in Cornwall. You got some massive ones and some much smaller ones. Not very many flats, which is interesting. Interestingly, most people, if you like, live in a semi-detached 1950s home. That's the most prominent housing type in the UK. That's quite interesting. And again, the colours are the same. So the greens are all sort of fine to put a heat pump in. Oranges, probably you'd want to make a change before you did. Red, it would be more tricky or costly. Good. So then we could look at making changes to the homes and how that affects things. So the work we did in this case was to create a model of some individual homes which could run thousands of iterations. So we don't really know what people are going to do in their homes. And there's lots of different changes we can make, and there's lots of variety on the quality of that. So this is it's called a Bayesian analysis where you choose all the different variables you want and you give it a range. So for example, wall insulation, the range is do nothing to 120, 140 mil of insulation. So people will land somewhere between that. And then for each of those variables, we give it a profile. So we say, okay, either it's normal distribution or it's a flat distribution or whatever. And then we run it and it randomly assigns all those different variables. In this case, we did 5,000 iterations of a home. And it gives you a sort of pseudo distribution, sort of fake distribution, but it tells us the risk and what would happen. And so this sort of shows you again where homes sort of go. So this is a small house with cavity walls. All homes are in the sort of safe zone. But if we go to a larger house with solid walls, actually a lot can be in the safe zone fairly simply, but we do have a sort of longer tail and homes getting riskier even if we make some of these changes. So yeah, just to give you a bit of a flavour on for an area, Cornwall warmer, but certainly sort of heat pump ready on the majority. I only picked Cornwall because they're the ones who've paid us to do it, so we haven't got it for any other areas. But that's interesting. So good. So that's sort of retrofit picture. And as I said, really, what matters for UK wide and net zero is electrification. So, and I'll come on to that, but that's the sort of piece to remember. So then we come back to Passivhaus, which we deal with mainly with new homes, but we do existing homes as well, and thinking about how that helps. So one problem with focusing on electrification of heat, which is likely to be where a lot of the grants and financing land certainly from government, because that's their priority, is we could forget about the people. So we could forget to try and make their homes better. When we've tried to do this sort of thing in the past, people don't necessarily want something that you think is better. We go and say, oh, we'll give you this free loft insulation. And they say, I've got a collection of Matchbox cars in my loft and I don't want you to touch my loft. Thank you. I don't want this insulation. So that happens. That sort of hoarding bit, that sort of practical people thing is the bit which is the barrier, even if it's free. And actually in other countries, they pay people to do it because they won't do it if it's free. So that's difficult. So the people part, for Passivhaus, it says, well, actually homes are quite rubbish. Even new build homes, we still have mouldy showers. People have poor air quality. There was a horrific case last year of somebody dying and it being directly associated to poor air quality in their flat. And that's just wrong. It's 2024. We should have hoverboards. How can we have mouldy houses? So it says, okay, comfort and air quality, we can just make it better, loads better. So that's the first thing it says. And in a retrofit environment, that's really interesting. We can, by doing some fabric efficiency, we can help the grid response and switch people's heating on and off without them noticing, which I'll come back to. So when we all plug our cars in to charge them and want to put the kettle on, the heat pumps can all turn off. So that's interesting. We can only do that with some energy efficiency. Delivering it, so I mentioned the Matchbox cars in the loft, but also actually a lot of construction is built quite poorly. And we talk about in the construction industry the performance gap, which is the difference between optimistic energy consultants like me guessing what's the building's going to use in terms of energy, and then when we measure it, it's like double if we're lucky. So there's obviously a problem there. Our model's really broken. And Passivhaus has done a lot of effort to work out why that is. And actually with a Passivhaus model, sometimes we overestimate, sometimes we underestimate. There's a margin of error. It's quite a good model. So that's sort of showing us that. Tells us how to manage that construction quality, that everything matters on the whole house. We can't just cherry pick different elements. We need to have a sort of whole house plan. It's good. And then the last thing it does is, we don't want to add more retrofit problems. And unfortunately, that's what we're doing. We've had projects. We've retrofitted a 2011 build. That's the newest we've ever retrofitted. I wouldn't be surprised if we soon have some 2020 housing or estate properties on the books as well. So yeah, let's not add to the problem. Good. So I'll tell you, that's sort of a bit about retrofit. Now I'll tell you about Passivhaus certification sort of quite separately, and then I'll touch on where they overlap. So certification, we see it for new buildings as a sort of simple formula that to get zero carbon, we need some energy efficiency, fabric efficiency, which Passivhaus delivers. And as I say, it's the outcome we're interested in, but Passivhaus is a great method to get there. Heat pump, low carbon heat. Actually, in the Passivhaus building flat, smaller properties, we can get away with direct electric and still have very, very cheap running costs, much simpler systems, and which is good. And then some renewables, either on the building or off the building, gives us the zero carbon we're after. So that's a sort of simple formula linking Passivhaus and net zero. I talked about the electricity grid. So this is just that peak demand side management and showing how it might work. So in a typical home, because the building cools down very quickly, we need to heat when you're present. So if you're in your house, you switch the heating on. If you're out the house, you switch it off and the building cools down. In a Passivhaus home, or even one with very modest levels of energy efficiency, so in my home, I actually heat constantly. I just maintain the temperature all the time, and I trickle heat in when it's needed. And that's actually a more efficient strategy when you've got a certain level of energy efficiency. And what that means is we can move when we're trickling that heat in. And that might be practically, that might be either done, you know, centrally by signals from the grid, but more likely it will be a market system. So you're already seeing that with Octopus Energy, who've got very dynamic tariffs, which operate on a sort of half-hourly basis, or it might even be less, time step might be smaller than that. And you pay for the minutes you're buying the electricity. So if you heat when the electricity is cheap, it's very much within your interest. So you can sort of move the buying. And actually last year in January, the prices were negative for quite a lot of January because there was so much wind, they were trying to dump it. So that's interesting, negative pricing. To put even more of their money where their mouth is, Octopus have got, for new homes, zero bills contracts. So they're saying, if we come and install your heat pump, and if we install PV, and you've got a certain level of fabric efficiency, we'll put a controller in there, and you basically pay us to keep your home at 21 degrees all the time, and we'll turn the heat pump on and off, and you don't pay any bills. So you know, that's how much the residents, the homeowners' energy consumption is worth. It's worth money. So it's worth them doing it because they can dump wind power on you when it's negative cost. So that's that sort of dynamic system starting to happen. That's really interesting. So Passivhaus allows you to do this to extremes. You know, in a school, Passivhaus applies to all buildings. Or all buildings with heating. In a school, you'd quite often have like an N+1 heating system. So you'd have two boilers in case one failed. You could run the other one. Passivhaus, we don't have that because if the boiler fails, they might not notice for a week. Yeah, it will just trickle on at the same temperature. So the sort of fabric efficiency is acting as that buffer. Good. Cool. So this is that linking that house diagram retrofit to the practical things that Passivhaus does. In a building sense, it's really, really simple, and you sort of start to wonder why we're not doing this already. And also, cost-wise, I'll come back to cost, but it's mainly adding air void, you know, adding an air void and doing the things which we're already paying for well. So that's the sort of main moves it makes. So excellent insulation is an obvious one. Interestingly, Passivhaus accounts for the surface area of the building. So in our building regulations, we have a set, there's a U value, everyone meets the same U value, it's fair. In Passivhaus, it says, if you're in a massive block of flats and you've got very little exposed surface area, you need less insulation. Yeah, which is true, physics-wise, true, you stay warmer. Elephants dead elephant cools down much slower than a dead mouse. That's the sort of physics of it. So you're in Passive House, if you've got really good, we call it form factor, surface area to volume ratio, you might actually have, in the extreme case, you need less insulation than the building regs say. And then for a bungalow detached in Scotland, you need maybe like a lot of insulation, 500 mil, which begs the question, should you be building bungalows in Scotland? Maybe not. Maybe we should attach them together. So there's that sort of link of the sort of physics with it. So insulation flexes with the exposed surface area. And we've got glazing, go for triple glazed windows in pretty much the whole of the UK. Only some very small areas is double glazing accepted. And that's mainly due to comfort. So what it's saying is that we feel comfort in the environment through roughly an average of air temperature, which is obvious, but also radiant surface temperatures. So our exposure to radiant temperature, and our operating temperature is roughly halfway between those two. So if we can increase all the surface temperatures, then it means we can lower the air temperature, which means we pay for less heating for the same comfort. So this is quite hard to visualize. Imagine you're in a 1930s school, or let's say a 1960s school, and there's loads of glass and it's all single glazing and you're sitting next to it. You will be cold, even if the heating's cranking and it's 25 degrees air temperature, because that glass is so cold. The opposite is you're in Siberia and it's -30 outside, but it's sunny. You go outside, you've got the radiant heat of the sun, you don't feel as cold as -30. So that's sort of what's going on. For Passive House, the crux of that is to get the surface temperature high enough in the UK, we need an extra pane of glass, which is where the triple glazing comes from. So we're just pushing the performance of the glass much closer to the wall. So that's where that bit comes from. Quite carefully sizing those as well. So they are worse performance than the wall still, so there's a heat loss, but we get some solar gain, so there's sort of net balance there. Good. So that's the sort of, coupled with thermal bridging, which is junctions. That's the puffer jacket, the woolly coat around you. The other two are around air movement, and this is really, really critical. And for existing buildings, this is often where we forget. We don't do anything about it. So the two, we're both of talk air tightness and ventilation, both talking about air movement into the building. So in winter, you've got cold air outside, that will find its way into the building. Plus we've got people inside who need some degree of, well, they're basically making smells and moisture, which needs removing. So we're going to have some air movement between the two. And we split those, we call one infiltration, which is basically unwanted air movement, and the other ventilation, which is air movement we want. And the idea is you can control ventilation, but you can't control infiltration. So ventilation could be opening windows, it could be trickle vents. In an old house, it just happens through leaks through the windows and maybe a chimney. So we haven't really had to think about it. And that old strategy of pumping loads of heat in and letting it all blow through the home is quite wasteful. So following a lot of logic, we get to a state where in winter, it makes a lot of sense to have quite a lot of control over the ventilation you're bringing in. And even better, if you take it through a fan, you can get heat recovery on it. So you can have a heat exchanger, and it means you only heat, say, 10% of the air you're bringing in. Practically for our homes in the UK, that means the air quality is a lot better. So I've actually got an MVHR in my house I installed, and I get flat relative, I'm in Brighton, I get flat 60% relative humidity, pretty much all the time. And I still can open my windows when I want to, when it's too hot, or I want more fresh air. So you just don't have that. Cool. So air tightness, just unwanted. When I shut the window, when I'm closed up, when I zip up my coat, I don't want air movement. So air tightness is the test to get there. When I do, I want it to be controllable. So I want an opening vent, I want an opening window, an opening doors, small fan, whatever it is. So that's the difference. So Passive House says most heating climates, you're going to need heat recovery, or it's better with heat recovery. Cool. Good. So I use Passivhaus a lot as just a proxy for low energy buildings, energy efficiency, quite broad things. Actually, it's a certification standard. So you can certify buildings to the Passivhaus standard. And this tends to be a bit of a mix of single homes. So people building their homes for a long period of time, which is about maybe, I don't know, 10% of the market in the UK. Most of it is council housing, housing associations, social landlords, building with some social purpose. And then the other part of the market is mainly in education, so schools, universities, and then mixed in, there's a little bit of private sector. Interestingly, the common theme across all those sectors is they are all going to own their building for a long time. Yeah, so that's the common theme. Anyone who's going to own their building for a long time is interested in Passivhaus because it's about operating costs, comfort, user satisfaction. That's quite interesting. So we've got this standard. It does two things for a client. It provides a target. It says this is what good looks like, and it's a hard target. You can't go past. There's a few different numbers, but that's the requirement. But more importantly, almost, it provides a process to get there. So it's essentially a quality assurance process, quality check of the design, quality check of what's happened through construction, and updating an energy model at the end. So that's the two things it does, the requirements and also the process, how to do it. From a client's point of view, particularly estate owners or landlords, it's useful because it's off the shelf, so they can put Passivhaus in their contract requirements, and then the building contractor has to do all these different things, and there's a method to police it. If they don't do that, they have to write a special way to make sure they're getting what they want. So that's useful as off the shelf. Okay, good. So these are pretty nationwide. There's probably in the region of 2,000 individual sites certified to Passivhaus or in the process of certification. These are our projects that are live. The green ones are certified, the purple ones are in progress, and the red ones are on site. So we're national. We focused on the UK. We're not really interested in work elsewhere because I like to go to the buildings. I want to know what we're looking at. And the sort of projects, this is the biggest one. This is in Bristol. This is very brutal Passivhaus, big blocks. Let's put as many students in as we possibly can. But really, actually, quite a nice site and lovely facilities, lovely rooms. So it's at University of West of England, certified in when was the last block was May, I think, or June. So that's sort of one end of the scale. Or another block. And this is a secondary school in London. It's not a particularly great photo of it. It's a really nice school on quite a main road near St Catherine's Dock, so in Wapping. So that's sort of housing, and then also a lot of housing, which I don't think I've put a photo in, which is a bit of a mistake. But yeah, so that's sort of buildings. So sort of process, I didn't quite know whether anybody was in the construction industry, but this might be interesting as a quick slide. I said it was a quality process. From a manufacturing point of view, it's the quality process up to the factory gate. So what we're interested in is all the activities that happen before the building's completed. Once it's completed, handed over to the user, we need to do more work, probably to optimize it. But Passivhaus is just the QA bit in the factory, if you like. Factory being the building site. So that's the part it's dealing with, to try and catch quality issues. And we're trying to catch them as early as possible. And these are really simple things, like you've assumed this door U value. There are no doors on the market that can achieve that U value. That's the sort of level we're talking. So it's very, very, very basic stuff. It's just tying things together on quite a big scale. How we do that is most of the time through a spreadsheet, massive spreadsheet. I think there's about 50 worksheets, which seems very, very basic. It's very open book. So one of the problems that we found with building simulation is very, very sophisticated software with very, very little validation and an awful lot of assumptions with no evidence behind them equals rubbish results. So what Passivhaus does is opens that all up and says, we're doing simpler modelling, but we know what the assumptions are, and we're being very, very careful about where the evidence for those comes from. That's what it's sort of focusing on. It does that through what's called the Passivhaus planning package. It's a big spreadsheet. You can think of it as a cost plan. So we have a cost plan for money. We write down everything that we think is going to be there. We put a value to it, budget initially, and then by the end we know what we've got and we know what the final value was. In Passivhaus, we put an energy budget against everything, and then we work through it. And at the end, we know what everything is, and we've got the final value. And we sort of work through that with Passiv with the PHPP. So that's it, and it gets complicated. So this is a building in Oxford for university, which is big. You know, it's like 18,000 square meters, and we're putting it all in a spreadsheet. You know, who would have thought it? 2024, there's meant to be flying cars. We're putting things in spreadsheets still, but it's the best way to get it. Part of the reason for that is this. This is everyone we've talked to on that project. There are a lot of people involved in building projects, and these are only the people who are involved in energy. So there's sort of, you can imagine how wild this goes. So we're in the middle here. These are the people we talk to most. These are the people we talk to maybe on a monthly basis, and then other people who we've had less interaction with. But that's just one building project, and that's really only the design side of it. Lots of these sites have probably got a churn of like 100 people a month coming through. So you've got to communicate all that information to loads of different people on loads of different levels. So it's very hard to communicate some of this stuff. Hence the need for some simple bits. So yeah, that's that building. The detail, just sort of thinking about what Passivhaus is teaching us. It teaches us that detailing matters. So again, going back to my coat analogy, if you buy a sort of super duper Arctic coat, it has a little flap that goes over the zip. It's because the zip's like a thin bit of insulation and it lets out more heat. And we have loads of those on buildings. So this is some concrete piles coming through. It's an extra heat loss for the building, which we need to account for and include in the model. So we go to quite a lot of detail, all the junctions, how much heat's going through, and some finite element analysis, trying to simplify the junctions so that we can use modeling tools. But I just wanted to, I quite like this sort of thing. It looks that's the detail top left, which is basically some rectangles. We do 3D as well, but it takes ages to simulate. We try and simplify it. I mean, it's good enough because on site it's concrete and it's wet and they're cutting it with a handsaw, and the tolerances are terrible. So it's always a simplification of what's going on. Effort, and this sort of detail ends up with 10 people standing around a hole saying, "Is the insulation stored well enough?" Cool. I won't go into document management, but you can imagine that many people on site. It's difficult. So just the quality on site thing, just getting across the insulation install is generally poor. It doesn't achieve what it's meant to on the packet, and that's pretty much all due to gaps between the board or moisture getting in. So we spend a lot of time going to site, agreeing upfront what it needs to look like, getting a little mock-up, taking photos, and this is a primary school principle for achieving quality. You can't do a good job unless you know what a good one looks like. Waggle principle. So primary schools, they'll do this as well, show you this is what we want it to look like, and then you go along and do it. And we do the same things on construction sites on a more complicated basis. Cool. So that's the end of that bit of the presentation. I didn't put my slide on Enefit, but the link between the overlap, which is quite a small overlap between retrofit and Enefit, retrofit and Passivhaus, is there's a retrofit specific standard called Enefit, which is same process as Passivhaus. The trouble with it and the trouble with Passivhaus is that they are very, very, very extreme remodeling almost of the building, which needs all those things, all those levels of insulation I've shown. And for some buildings, the big blocks of flats, larger buildings generally, which are really much at the end of their life, it's quite a good fit because it says we're going to upgrade this to new building standards, basically. We're going to bring this up to new building standards, strip it back to the concrete frame, maybe go there. For everything else, actually, all we're getting from, well, not all we're getting from Passivhaus, the value we can take for Passivhaus is actually how to do it. It's not the targets themselves. It's probably not even the certification method. It's what lessons have we learned from trying to do this over the last 20 years? Where have we gone wrong? What's the management side of it? What do we have to get in to make sure that it happens well and we achieve the sort of good outcomes we want, which is better buildings? Cool. So my summary was the retrofit side is about electrifying heat wholly. We must remember not to forget. We mustn't forget internal comfort and air quality. So that's that big headline. Passivhaus doing two things. It's a limit, a requirement, and also the process. It's that process of quality assurance, checks how we get there. When in doing energy efficiency, we're reducing peak load on the electricity grid. It's the simplest way of thinking about it, but that's a really, really, really valuable thing. And it's got valuable. It's got a value to it. It's got some money associated to it, and that will become more and more important in the future. And then lastly, delivering construction quality is very difficult. But if you put a bit of insulation under the floor well, it will be there for, 100 years, maybe 200 years. No maintenance costs, just sits there, does its job. Magical. So, do it right first time and we won't have to go back. Cool. So, thank you.
Thank you.